Welcome to the part 2 of our exploration of engineering graphics beyond standard reference planes. In technical drawing, we often encounter planes that don't align with traditional horizontal and vertical planes. These unique planes are classified into two main categories: perpendicular planes and oblique planes. Perpendicular planes are those that sit at right angles to one reference plane, but are inclined to the other. Oblique planes, on the other hand, are inclined to both reference planes, creating more complex geometric representations. Let's dive into the world of non-standard planes in engineering drawings. Perpendicular planes are fascinating geometric constructs that sit at right angles to either the horizontal or vertical plane. A classic example is a vertical plane that's perpendicular to the horizontal plane, but inclined to the vertical plane. Oblique planes introduce even more complexity, with surfaces that are slanted across both reference planes. These planes are critical in representing real-world structures like mechanical components and civil engineering designs. Understanding traces is fundamental to representing planes in engineering graphics. Traces are the points where a plane intersects the principal planes, horizontal plane, vertical plane, or both. The horizontal trace represents the intersection of the plane with the horizontal plane. Similarly, the vertical trace marks where the plane meets the vertical plane. These traces are essential tools for defining the orientation of complex oblique planes. The inclination of a plane is a critical aspect of its geometric representation. Engineers specify two key angles: the angle with the horizontal plane and the angle with the vertical plane. These angles help us precisely describe the plane's orientation in three-dimensional space. To simplify complex plane representations, we can convert oblique planes into auxiliary planes. This transformation makes it easier to visualize and measure the plane's characteristics. Projecting points and lines in non-standard planes requires careful geometric analysis. When a point lies in an oblique or perpendicular plane, it will have specific projections on horizontal and vertical planes. The process involves marking the plane's position using its horizontal and vertical traces. We then project the point perpendicular to both reference planes. Similar techniques apply to lines lying within these unique planes. Let's explore projection techniques for perpendicular planes step by step. Begin by drawing the traces of the perpendicular plane carefully. Next, project points or lines onto the horizontal and vertical planes as appropriate. Use geometric relationships to complete the projection accurately. This method ensures precise representation of objects in non-standard orientations. Projecting objects in oblique planes presents more complex challenges. Start by determining the horizontal and vertical traces of the oblique plane. Draw projections of points and lines within this uniquely oriented plane. Auxiliary planes become crucial for finding true lengths and shapes. Mastering these techniques is essential for advanced engineering graphics. The conversion to an auxiliary plane is a powerful technique in engineering graphics. Begin by rotating the oblique plane to make it parallel to the horizontal or vertical plane. Perform your projections in this simplified auxiliary plane. Then carefully convert the results back to the original plane's orientation. This method simplifies the representation of complex geometric configurations. Let's solve a practical problem involving a point in an oblique plane. We'll work with a point inclined at 30 degrees to the horizontal plane and 45 degrees to the vertical plane. First, mark the horizontal and vertical traces of the oblique plane. Draw projections of the point based on its precise location within the plane. Use auxiliary planes to calculate exact distances with precision. Our next challenge involves determining the true length of a line in an oblique plane. We'll start by projecting the line's endpoints onto horizontal and vertical planes. Then, we'll transform the plane into an auxiliary plane for accurate measurement. This technique allows us to measure the true length of the line. Such methods are crucial in engineering design and technical visualization. Engineering graphics extends far beyond theoretical concepts. These projection techniques are critical for understanding real-world objects with inclined surfaces. From roofs and ramps to support structures, these methods help engineers accurately represent complex geometries. Mechanical and civil engineering designs rely heavily on these precise visualization techniques. Understanding plane projections is key to creating accurate and functional technical drawings. Welcome to the fascinating world of solid projections in engineering graphics. When a plane is parallel to the horizontal plane, its top view shows its true shape, while the front view appears as a line. When it's parallel to the vertical plane, the front view shows its true shape, and the top view appears as a line. This helps us accurately represent the plane's orientation in drawings. Projection of solids involves representing three-dimensional objects in two-dimensional planes. Solids are classified into polyhedra like cubes, prisms, and pyramids, and solids of revolution like cylinders, cones, and spheres. These projections are created in either the first quadrant, first-angle projection, or the third quadrant, third-angle projection. The axis of the solid is a crucial feature, as it determines how the solid is oriented relative to the horizontal plane HP, vertical plane VP, and profile plane pages. This method is essential for accurately depicting the dimensions and shape of solids in engineering drawings. Our first projection case involves a solid with its axis parallel to one plane. In this scenario, the solid shows its true shape in the plane to which it is perpendicular. Imagine a cube resting on a horizontal plane or a cylinder with an axis perpendicular to the vertical plane. The projection steps involve drawing the true shape and projecting points using perpendicular projectors. This method provides a clear and accurate representation of the solid's geometry. Now we'll explore solids with an axis parallel to one plane, but inclined to another. Picture a prism lying on its base, with its axis inclined to the vertical plane. The key is to draw the true shape on the parallel plane and then project its points onto the inclined plane. Careful attention must be paid to the alignment of visible and hidden edges. This technique is especially useful for representing slanted structures like ramps or beams. This projection case represents the most challenging scenario. We're dealing with a solid whose axis makes an angle with both horizontal and vertical planes. Accurate visualization becomes critical to represent visible and hidden details correctly. Engineers use auxiliary planes to simplify the solid's orientation. The goal is to project the true shape and then convert back to standard projections. Our final projection case focuses on the axis perpendicular to the profile plane. Here, the axis is parallel to both horizontal and vertical planes. This method is particularly useful for creating side views or profile perspectives. The true shape is directly visible in the profile plane. Such projections are crucial for cross-sectional views of machines and architectural components. Understanding the nuances of visible and invisible edges is crucial in technical drawing. Visible edges are represented by solid lines, while invisible edges use dashed lines. The key is to identify the observer's point of view carefully. Analysts must determine which edges would be obstructed from view. This attention to detail ensures a comprehensive and accurate representation. Two powerful techniques help engineers simplify complex projections. The rotation method involves rotating the solid around an axis to simplify projection. It's particularly useful for solids with axes inclined to both principal planes. The auxiliary plane method introduces an additional reference plane. This helps determine true shapes and dimensions with greater precision. Let's solve a practical projection problem with a cylinder. We'll work with a cylinder whose axis is inclined to the horizontal plane. The process begins by drawing the top view of the base circle. Next, we'll incline the axis and project it onto the vertical plane. Finally, we'll add both visible and invisible edges to complete the projection. Our second problem involves projecting a pyramid with a complex orientation. We'll start by drawing the base on the horizontal plane. Then, we'll use an auxiliary plane to rotate the pyramid. The goal is to project the apex and edges onto the vertical plane. This method demonstrates the power of auxiliary planes in challenging projections. Engineering graphics projection techniques have wide-ranging practical applications. They are essential for designing mechanical components with complex geometries. Architectural modeling relies heavily on these precise representation methods. From piping systems to intricate machinery parts, these techniques provide critical visual insights. Understanding solid projections is key to translating 3D concepts into 2D technical drawings. Welcome to the fascinating world of surface development in engineering graphics. This process involves creating a flat, two-dimensional layout of a three-dimensional object surface. Surface development is crucial in manufacturing, especially for working with sheet metal. It allows engineers to understand the precise geometry of complex objects. From ducting systems to packaging, this technique has numerous practical applications. Surface development serves multiple critical purposes in engineering. It's primarily used in fabrication, creating precise templates for sheet metal parts. The technique provides deep insights into the three-dimensional geometry of objects. Industries like packaging, tank design, and industrial manufacturing rely on these methods. It's an essential skill for converting complex 3D shapes into manageable 2D layouts. Parallel line development is ideal for solids with consistent, parallel edges. This method works perfectly for prisms and cylinders with uniform characteristics. The process involves unrolling the surface along a generator line. Each edge is represented as a straight line in the final layout. A cylinder's development, for instance, becomes a simple rectangular representation. Radial line development focuses on solids with a central apex. This method is perfect for cones and pyramids with radiating geometries. We use the apex as a critical reference point. Radial lines are extended from the apex to the base perimeter. The lateral surface is developed as a precise sector of a circle. The triangulation method tackles the most complex surface developments. It's ideal for irregular shapes with challenging geometric configurations. The key approach is dividing the surface into a series of triangles. Engineers carefully calculate and represent each triangle's dimensions. This method provides flexibility for surfaces with curved or irregular geometries. Let's explore surface development for prismatic shapes. Right prisms feature a replicated base in the layout. The lateral surface appears as rectangles corresponding to the number of faces. Oblique prisms require additional considerations for their slanted edges. Trapezoidal faces are used to account for the unique geometric characteristics. Cylinder surface development requires precise mathematical considerations. Right cylinders feature two circular bases in the layout. The lateral surface becomes a rectangle with specific dimensional requirements. Height matches the cylinder's actual height, which corresponds exactly to the base's circumference. Cone surface development follows a fascinating geometric principle. Right cones feature a circular base and a sector-like lateral surface. The sector's radius equals the cone's slant height. Arc length matches the base's circumference exactly. Oblique cones require more complex triangulation methods. Pyramid surface development reveals the shape's fundamental geometry. Right pyramids replicate their base shape in the layout. Lateral surfaces appear as triangles converging at a single apex. Oblique pyramids demand more nuanced dimensional adjustments. The triangle's dimensions are carefully modified to reflect the apex's inclination. Surface development follows a systematic, step-by-step approach. First, carefully understand the solid's fundamental geometry. Determine whether the solid is right or oblique in its configuration. Identify all critical edges, base, and curved surfaces precisely. Choose the most appropriate development method based on the object's characteristics. Let's solve a practical cylinder development problem. We'll work with a right circular cylinder measuring 10 centimeters in height and 5 centimeters in diameter. The lateral surface development becomes a rectangular layout. Height remains 10 centimeters, while width calculates to pi times the diameter. We'll add 2 circles to represent the base, completing the comprehensive development. Our next challenge involves developing a right cone. We'll use a cone with a base diameter of 6 centimeters and a slant height of 10 centimeters. The development process creates a precise circular sector. Radius matches the slant height exactly at 10 centimeters. Arc length calculates to pi times the base diameter. Surface development finds applications across multiple engineering domains. Sheet metal fabrication relies heavily on these precise techniques. Packaging design transforms complex 3D concepts into manageable 2D templates. Industries like HVAC use these methods for designing ducts and tanks. CNC machining depends on accurate surface development for component creation. We've journeyed through the fascinating world of engineering graphics. Remember, precision and creativity go hand in engineering visualization. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.